Hello, good afternoon. Thank you for joining me today for this live stream. We're going to be going through some RAG pipelines. We're going to be going through some Python libraries, and we're going to be going through some very interesting use cases today. So I'm Richmond Alake. I'm a developer advocate over here at MongoDB. And for those of you in the chat that are watching this live, feel free to tell me what you're tuning in from. Also, you can tell me what you're building with AI, your use cases as well, and you can also share what problems you've been going through this week. I've been going through some problems when I'm building my AI applications, and we can talk about those and maybe troubleshoot live. Who knows? So today we are going to be going through use cases within the finance industry. But before we focus on that, before we get started, let me actually start sharing my screen and I'll actually talk about some basic concepts. We're going to talk about RAG, we'll talk about the AI stack, we'll look at some diagrams, and we'll try to paint the picture, then go straight into our story. All right, let me start with sharing my screen. So over here, we can put this in slideshow mode. So always start my presentation with explaining what MongoDB is and where it fits within the nature of your application stack. So MongoDB is a developer data platform, and within this platform, we enable developers like yourself to access the MongoDB database feature through MongoDB Atlas. And with this database feature, you can essentially build some form of memory store vector database for your RAG applications or for your semantic search applications. And those of you that are exploring AI agents in agentic system, you can see MongoDB as that memory provider for your agentic system. But within MongoDB, it's very different to other databases. MongoDB is built and the way we store data is built and centered around the JSON schema, but an extended version of JSON, which is the BSON schema, which is binary JSON. And this allows for more storing of different data types. We'll talk about the document model in later. But the document model, I say later, we're talking about it now. Well, the document model essentially can store any key value store data objects. So, for example, we have something that most developers would be familiar with. This is a JSON object, right? You have a key, you have a value. This is the pattern, and you can also have a key value where the value is an array. So that's a different data type. Or with the extended binary JSON, you can have different data types such as dates as well. So this is how data is stored within MongoDB. Very familiar. JSON is used across as a data as it's a common data structure used across different programming language. So it's very familiar. You're bringing that mindset that you use on the application layer. You're going to be bringing that into the database layer within into that database platform or database layer with MongoDB. So deep diving into the document data model. To understand the document data model, let's go a bit higher level and talk about what a data model is. And in a nutshell, data model essentially is a way of visualizing how a data object should be represented, right? It's a very abstract representation of a data object. So for example, we might have an e-commerce store and we might have a customer data, and a data model could include what objects, what attributes are in these customers and other areas or other entities that this customer object is going to interact with. So this is a data model. So if you bring that thinking together, you can conclude that a data model is a logical and systematic instruction for the structure, just like this, for the structure and organization of data. And this is data that resides within any information system such as or storage system such as a database. But one thing is a data model is just an abstract representation, it's not the data itself.
So when we were talking about the data itself, we'll be talking about something like this. So this is another example of a JSON schema or a JSON data type. So what we see as the key value pairs, ID, and we have the attribute ID, we have the ID actual ID value as a string. And this is a data object that represents a customer that we modeled over here. So this is a JSON object, and this type of structure is referred to as JSON, and we can store it in MongoDB using the document data model. So, but what is a document, right? A document essentially is a way of storing data and structuring data, but more formally is a systematic and logical realization of a data object. So you might have an object in real life and you might have a digital representation of it. Then you can construct that digital representation as a document, as we've seen here. But a document is flexible, and we can actually represent different data objects with complex data structures. So if you then put the two words together, we can understand what a document data model is, which is a logical and flexible framework for organizing and representing data in a storage system. It can store complex and nested data structure, and that's what a document data model is. And generally, we're going to see data we can store with a document data model. Data we could store with the document data model are JSON, like we've explained, BSON, like I've touched on, also XML. Generally, key value pair. You can also model graph data using the document data model as well. So it's very flexible but very powerful. So that is a very high level overview on how we store data in MongoDB. Now I'm going to talk about the AI stack, and we're going to go through some of this a little bit quickly so we can get to the key part of this live show.
So the AI stack is essentially a bunch of tools that are coming together to help you, the developer, build the best AI application you can. So these are the tools, the libraries, the frameworks you're selecting to essentially build out your AI application. So what tools are you building? Well, you're building things such as chatbots or chatbots powered by RAG or AI agents or agentic systems. These are the form factor of AI products we see today within the Gen AI space. But
the AI stack, if we just look at it from a low level view, consists of a programming language and model provider. This can be OpenAI or Anthropic, whichever ones. Or you could have the LLM framework, which could be LangChain. It could also be Llama Index or AStack. But MongoDB lives in this part of the stack, in this operational and vector database layer of the AI stack. Then you have other parts of the stack of the AI stack. There's a link here where you can get some more information on the AI stack itself. So we're almost getting there. I want to covering the basics. So let's cover RAG. Then we can then talk about the use case and what we're going to be building today. So RAG, Retrieval-Augmented Generation. And what that means is we're essentially supplementing a user query with some retrieved information and passing that into an LLM to at least get a relevant response out of this LLM. Now, that in a nutshell is what RAG is. To sort of like give you context, normally when you interact with an LLM without RAG, you're giving it a query to, for example, give me recommendations for my next holiday. And the LLM might just give you some answer from its parametric knowledge or knowledge that it has been trained on. And it might tell you, hey, Tokyo, Japan is a popular holiday. You can also consider London. That's my bias creeping in there. I'm based in London. So, and that is sent over to the user. But there is no personalization because there is no data to actually personalize that. There's no data that references this user that is passed in. So this is just generic. Person A and person B would get the same response from this LLM. But when you start to bring in some aspect of data and more specific and proprietary data or user specific data, you can start to tap into the real power of LLMs, which is that response synthesis, but also generating a response that feels very natural, but is grounded by the data you've provided it. So I ask it for another holiday recommendation, and what it gives me is a more grounded response, more relevant response if you look at the data. So for example, it says, hey, based on your preference for adventure and cultural experiences, and that's been stated over here, adventure and cultural. So that's what RAG is. We're just retrieving information to supplement with user query. Now, what we're doing with RAG is effective, basically information retrieval, and we're trying to retrieve relevant data, not just any data, relevant data. And relevancy is determined by maybe the context that the query is based on, or the current session or the application. So, and there are different ways you can retrieve information. So you can retrieve information from vector search, which is basically searching by meaning, or you can do standard old text search, or you can combine both and you can do hybrid search. So with vector search, what you have is essentially you have an embedding, and you pass in your query, and you have an embedding model that you actually pass your query into. You get a vector that you can then conduct vector search functionality against all the embeddings you have in a database or in a data store somewhere. And text search is just searching by text. And then hybrid search is combining both to get some you're combining the best of both worlds with some tuning. And all of this is enabled on the MongoDB database. And I just kept an image here to actually give you guys an understanding of what a RAG pipeline is, what it looks like. So we have this ingestion process over here where we have a data source, we prepare our data, then we embed, we generate some embeddings. Then when we're ingesting into a MongoDB database, we're actually passing in the embedding alongside the metadata. We're going to see all of this today, by the way. Then when we're conducting a query, we have the user asking a query, we have a user prompt, then we conduct a vector search to retrieve the relevant query. We get the relevant query from the database, and we pass that as additional context with the user prompt to the LLM. And that way we get a more grounded response.
So there's so many topics you can dive into when you're looking at each component of this pipeline. On the MongoDB Developer Center, we have several articles that talk about each of this topic, and we will be building more articles over the months. So I'm generally just going to go through this quickly, just so we can get to the good part. But I want to talk about the most important bit here, which is where you're storing your data and what are the topics you need to be thinking about. So developers like yourself are probably thinking about query optimization. Am I going to be using hybrid search? Or am I going to be using vector search? Or am I going to be using just text search? Some indexing technique, data partitioning and sharding. You're thinking about latency. How long is it taking me to get that relevant information? And some of you working in very sensitive industries, and also some industries are regulated, are thinking about security and compliance, which is going to be around the use case we're going to be talking about today. So going through the slides very quickly, just so I can get to the use case, we're going to be focusing on finance, and we're going to be talking about automated compliance pipeline. We're going to be building an automated compliance pipeline. It's not really automated, but you can get the picture on how to automate this. So what's the problem here? The problem we're trying to solve is there's a lot of banks around the world that get fined several millions of dollars, pounds, whatever currency in your country. And these fines essentially are a result of mishandling of transaction that violates certain policies. And you can see some of this fines are results of sanction violation, money laundering, risk management failures, or just fraud, essentially. So sanction violation, what that means is essentially you're basically facilitating, you're handling a transaction that a country might deem as that might not want to allow within a country. So for example, there are certain countries that within the UK, you can't essentially facilitate any transaction with, so do any international transaction with. And you can look up the list. This could be the same for your country as well. but also money laundering, risk management failures, and fraud. So all of this cost a bank or any financial institution several millions a year. Now imagine if you can solve this, if there is a way to detect transactions using a bit of LLM, using a bit of that large language model abilities, but also doing it in a way that is modern, in a way that actually enables scalability, and it can be automated as well. So that's what we're going to be talking about today. We're going to be solving a problem within the finance sector, and the use case is enhancing financial transaction compliance with an automated regulatory compliance pipeline. That is a mouthful. And compliance is said a lot in that sentence. But the solution is to build this pipeline, this compliance pipeline. And we're going to use RAG, we're going to use semantic search, we're going to retrieve data through meaning using vector search. And this system can be automated for those of you who are data engineers. When you see the code, you can start to think about how you can build some data pipelines with triggers and some automation features as well. So the solution we're going to build is going to be able to monitor transactions. So when we have an incoming transaction, we'll be able to look at the transaction and then compare it and against some policies within our database and see if there are any violations. And this might sound complex, but within the next 30 minutes, I'm going to tell you how, well, not tell you, show you how you can build it. If we're looking at flowcharts, for those of you who like a flowchart of how the system is going to operate, we're going to have a transaction as input. Then we're going to retrieve certain policies, and this could be policies from different countries. We're going to see examples of that in a database. Then we're going to use semantic similarity to actually see what policies match the transaction. Then we're going to do a compliance check. And this is where we're going to be using that LLM. And I'm going to leave it as a surprise what model we're going to be using, but it's one that is open source. Then we're going to have like a flagging feature and a little bit of a reporting, but that's in this demo, that might be a stretch. But we're not going to be generating any reports, but this is the flow of what you can do with this, a full-fledged system. Based on that, we can go into the code. But before we go in, I'm going to stop sharing my screen. I was just about to leave the studio there. There we go. All right, so I can go through some questions. So, hey, we got people from Brazil. Wait, that's you, Pedro. And we got some people asking, is it live? Yes, we are live. I'm waving my hand. That doesn't prove that we're live, but we're live. Is it good practice to store embeddings in the object itself as well? As should we re-render embedding every time a CRUD is performed? I'm not understanding that question, but you can store embeddings alongside the other attributes within a document. We're going to see this in a second. And yes, and do we re-render every time? Do we re-render the embedding every time CRUD is performed? No, we don't. We don't need to do that. So yes, we are live at Richmond. Yes, we are. I think store embeddings is a serious problem. So storing embeddings is a serious problem. Well, MongoDB has solved it. We can store embeddings alongside your operational and transactional data. So that problem is solved with MongoDB. So banks have a huge amount of transaction. How would you stream the transactions in? So like I said, there might be some data engineers over here, and you can actually have a bunch. You can actually have a bunch of pipelines, streaming pipelines that are basically listening for events from maybe a data source, your transaction data source. And if you're talking about scalability, MongoDB can handle that as well. MongoDB has a feature called stream processing. Let me see if I can I'll try to get some information on that and paste that in the chat as well. But let's get into the code. I've got 30 minutes to show you guys some magic. It's not really magic, but I'm emphasizing there. But it's going to be fun. So I'm showing my screen again, and I'm going to make this very big. Just so you know, all the code that is being shared over here is going to be accessible in this repository. So if you're watching the show right now, you're in luck, because I'm just going to paste the link in the chat right there, and there you have it. Go to this repository. Let me quickly tell you what this repo is. This is the Gen AI showcase, and it contains loads of cookbooks for you guys to play with. For example, the ones I'm going to be showing today. The code I'm going to be showing today is not on this cookbook yet, but right after this this live show, I'll be putting it up into this cookbook. So here we go. We have RAG. We have RAG notebooks. This is over 10 notebooks. We have agents notebooks. You can just run these notebooks and get a little bit of understanding of what people are talking about when they're talking about AI agents or agentic system, or with MongoDB. And some of these notebooks have a story, they have an article attached with them. But we also have some machine learning, just traditional machine learning notebooks for you to understand some other aspect of AI. For those of you who are new, AI is more than just Gen AI. So there is libraries like TensorFlow and PyTorch. They used to rule the world once upon a time. And we have some MongoDB specific notebooks that teach you how to build some complex queries as well. But this is a repository that you want to keep in your back pocket and share with your friends that are engineers, obviously, because we're just going to keep building this repository and adding some wealth of information here. So that is the Gen AI showcase. The link is on the chat, and you can put a star on this just to encourage us to keep doing more. And we're going to go back to this. So here we are with the code. And just to show you what we're going to be covering today, it's just 7 steps, right? And we're just going to be installing some libraries, and we're going to load some data, and we're going to create some data models with Pydantic. There is Pydantic in the title of this YouTube video. We're going to be using Pydantic as well, generating some embeddings, and then doing all the normal stuff that we spoke about in the presentation with a RAG. Then we're going to be looking at how we can enforce, how we can detect policy violation with Google's Shield Gemma, which is a variant of the Gemma models, which is an open model from Google DeepMind. And this particular variant of this model is been trained to enforce policies that you pass into it. So it would give you a quantification of a violation of a policy, and with some carefully crafted prompts. So we're going to see all of that today. When you get this notebook, after you're done with this live stream, or when you're watching this video, you'll be able to get a link to this notebook in the description of this video. But if you're obviously keeping this and bookmarking this page, you'll be able to see this notebook when it's ready. So we're going to go back to the code. We have the use case we spoke about, and we also spoke about the proposed solution. Then we're going to install a bunch of libraries. And I'm going to talk about these libraries very quickly. We have data sets. This is a Hugging Face library. We're going to be using some synthetic data that we have in the MongoDB Hugging Face organization. So we're going to be loading 2 data sets from there. We're going to be using pandas as well, which essentially allows us to create some Python data structures that enables ease of modification and visualizations as well. We're going to be using PyMongo to connect to our MongoDB client. And Pydantic, we're going to be using Pydantic for data validation and to create some data models that we want our data objects in our data set to conform to. And we're going to be using good old OpenAI for our embedding generation. And we have a bunch of other standard libraries like transformers, also from Hugging Face, to give us access to that Shield Gemma open model that we're going to be using today. You guys have probably heard of Gemma, but there's a Shield Gemma, and I'll show you how you can use that for your specific use case that involves enforcing policies. If you have any questions, please ask in the comments, and when I go back, I'll be able to answer them as well. The first one we're going to do here is you're going to need an OpenAI key. And one thing we're specifying here is we're not going to be using a GPT model. We're just going to be using the embedding model. I'm using the embedding 3 small, and I'm using the 256 for the dimension size. So the next step 2 is data loading. what we're going to be doing here is we're loading two data set, we're loading the policy data set, and we're loading the transaction data set. And normally there's meant to be a visualization of the data here, but we can go to Hugging Face and I can show you what the data set looks like. And so we can get an understanding of what we're playing with. And this is the MongoDB organization. You can follow or you can watch repos of this organization. I'll put this in the chat as well. Here you go. And that's the MongoDB Hugging Face organization. And I'm giving you this link because we have a bunch of data sets that you can experiment with. And some of this have embeddings with them. So you don't have to pay OpenAI. You don't have to give OpenAI your money. With giving them our money to help you. So we're going to be looking at two data sets here, which is the first one is this transaction data set. So we need a data set that contains transactions. For those of you that are trying to experiment with this particular use case, or maybe you work in a bank and you want to do some practice and build some POCs, and you don't want to use some sensitive data, come over here, download this data set, and you have a data set that contains some relevant finance-specific attributes. So this data set contains, each contains 200 transactions. And what we have here, one single transaction contains, I'm just going to zoom in here. One single transaction contains the timestamp, which is where the transaction was made. Also contains information of the sender. So this is the bank it's from, the country it's from, contains the information about the receiver, which is the bank it's going to, and the currency and the country and the name and the transaction details. So these are like information for financial transactions that you typically have in your traditional bank. And don't quote me, I've never been a banker, but I'm assuming this is what you would have. So the next data set is a set of policies that we can't view over here. It's missing the split, but we're going to see it in the code anyway. So now we could talk about Pydantic. In the notebook, I've specified why we're using Pydantic and why Pydantic is is good to use alongside MongoDB. But generally, Pydantic can enforce certain data structures that you want within your RAG pipelines, within your system. It ensures that any data objects are conforming to your data model, also down to the specific type, and then it gives you the ability to handle any errors or validate any incoming data against the expected type or the expected structure, and you could build custom validation errors as well. So over here, I'm actually building, I'll start from the bottom up. I'm building a policy model. So this is what a policy essentially looks like. Each data point in a policy data set is going to have a policy ID, it's going to have a country, a policy name, and other information associated with the policy, such as the regulations. This is the key part, right? So this policy is going to contain some restrictions, and then we're going to see what agency is enforcing it, so we know who's going to fine us. So yeah, this is just how we're enforcing a data model and ensuring that our data objects in our data sets conforms to this policy data model. And we have sub data models inside of this policy model. We have the regulation as another data model and the enforcement agency, and are all nested into this policy parent model, data model. So this function essentially converts a role, converts a data set within a data point within a policy data set into a data model. Wow, that's a hard sentence to say. So what we're doing right here is we're basically taking we have a row, and you take each row. This function is going to take a row from our data set, convert it to a dictionary, and then we have a dictionary representation of our data set. That's good. Step one. Step two, we're going to update the last updated field over here to wherever data is at the moment that we're doing this ingestion. And then we convert it into a policy data model that we've specified in the previous cell. Then we can ensure that every single policy that is coming in from this row conforms to the specified this model. And if there is like an extra attribute or a missing attribute, or well, none of this are required, but if there's a missing attribute or attribute that doesn't conform to the type, then there'll be an error that will get flagged up, and we can see over here that there's an error, and we can solve it. So this is the power of using Pydantic. It makes data validation easy. It makes enforcing data quality, or data. Yeah, it makes enforcing data quality easy as well. But some of you have noticed that Pydantic also follows this key value. This is a data model, but it's following that key value pair, which is what works really well with the document data model. So you can actually ingest any data created in Pydantic and ingest that into MongoDB. So we'll be showing that in this notebook. All right, so we've explained the rotor policy. Now we have a variable called policy objects, and now we're going to get all the policies, the data frame, and we're going to apply that function to all the data points. And what this does is it applies this function, rotor policy, and gives us a policy object. And we can look at the first element in this policy list, and we can see that we have this policy data model that we specified up here, and then we have all the attributes that we expect. So just for context on what a regulation or description of a policy would look like is this particular policy states that all transactions exceeding $10,000 must be reported to the National Financial Authority. I'm sure this is not like a real policy. I don't know. It could be. But this is something that essentially in this use case, maybe there is an audit being done for this financial company. And then in the audit, we saw a transaction that exceeded 10,000 and then it wasn't reported, then the bank could get fined. And essentially what we're doing now is we're building a system that can flag if there's been any breakage or if there's been any violation of this policy. And you can't have a human going through every single transaction that comes in through a bank. That would be a waste of time because you would not make a dent. But that's a general approach we're taking to modeling and creating models of the data we have in our data set. And we're going to do the same. So we've done it for the policies. Now we need to do the same for the transactions. So we have policies and we have transactions. Those are the two key data sets we're using. And it goes through the same step. This is the key transaction model, and we have all the sub-models, data models inside of it. We have a row to transaction. Sure, some of you are thinking, hey, Richmond, you could have made the row to policy and the row to transaction maybe use in a single function, but hey, making it as clear as possible. So we have a row to transaction, and then we do the same thing. This function converts each data point in the transaction data frame into that transaction data model. That way we have a transaction. And what does a transaction look like? It's very simple. A transaction has the name of the person making the transaction, the country they're from, the bank that they're using, and the payment, the amount of the transaction as well. $844,000 is a lot of money. Yeah, so we need to make sure that we're not breaking any policies when we're sending that. Now we can start embedding. We could do some embedding generation. And if you've built RAG pipelines, you probably know this step in and out. But what we're doing here is where we have a function that generates embedding. Into the function, we pass in a text. The text could be any text, string, or any form of data, essentially. And what we do is we pass that text into the embedding model. We're using the text embedding free small model, and we're using the 256 dimension. So it's very small, but powerful. So then this function extracts the embedding from what is returned from the OpenAI call, and then we store the embedding within each transaction and within each policy, because we embed
we embed some attributes in the transaction, and we embed some attributes in a policy because we want to do some semantic search enabled through vector search. So what we're going to do is we're going to prepare the transaction text. So this is the text we're going to use for the embedding. So you don't have to use all the attributes in your in a document to actually construct an embedding. You should probably be looking at your attributes and deciding which attribute or parts of my document actually encapsulate meaning and semantics, because we're going to be conducting a search that is based on meaning or semantics. So here we have a bunch of attributes we're using based on the transaction, and we have a bunch of attributes we're using based on a policy. And here we're simply doing this, and what we're doing here is we're adding an embedding to every transaction, and we're adding an embedding to every policy. Into the data point, in every data point, we're going to have an embedding attribute. We're going to see that in a second. And we've also accounted for this in our previous data model. So let me just show it. So you can see here, the transaction has an embedding. The reason why no validation error wasn't flagged up is because this is not a required field. It's optional. So you can start without an embedding, but then in later downstream processes, you can then generate your embedding and place it into a transaction object, and you will not get any errors. So scrolling down, we're going to create the embeddings for both the transaction objects and the policy objects. Now we have embeddings inside of each of the data point. I'm going to show you all of this over here. I've been logged out, but I'm going to show you all of this in a MongoDB database. So I'm just going to sign in. We're going to go through and we'll talk about some MongoDB specific operations. And I think we're doing well on time. So over here, MongoDB is your operational and vector database for your AI application. And in this notebook, you can register for a free MongoDB Atlas account, and you can go through this notebook and get things built by yourself and just go through each cell. So there's some instructions. This link take you to places for how you can set up your MongoDB database easily. And also, you're going to need a connection string after you've done step 1 and step 2. You're going to need your connection string, which is a URI that connects to your cluster, your MongoDB cluster. And your database is essentially within a cluster that we're going to be accessing through PyMongo. So over here, we're placing the MongoDB URI. And then we have a function that just creates a PyMongo client that allows us to access our our database and our collection. So this function is just this is just a standard function to make a connection to our database. And if we have that connection, we're just going to print out successful. So our database object is going to be assigned to a variable called DB. The database is going to be called financial rag DB. And the collections, remember we have 2 data sets, so we want 2 collections. That's going to be transactions and policies. So let me log into my MongoDB account to show you what this actually looks like. And when we see what this looks like, we can see what the embedding looks like. Then we could go into the data ingestion process, and we could talk about how we're going to be detecting any transactions that violates any of the policies that we have. So right over here, we have MongoDB. Just 1 second. Yep. So when you log into MongoDB, you get an overview of your account, and you can very quickly access a cluster. For those of you who are actually here for the first time, registering for MongoDB for the first time, you can just create a cluster over here. You're going to be visited with this page. And with MongoDB, you can create a free cluster. I've already used up my free cluster, but it's going to be a shared cluster. And you can actually place, you can actually use any cloud provider. So you can use AWS, you can use Google Cloud or Azure to host your MongoDB cluster. and you could choose the region. Essentially, you're choosing the region that is most closest to you. And you can also set some parameters, such as what clusters you actually want, which the tier of the clusters you want, the storage you want as well. But if you're using a free tier, you don't need to modify all of this configuration. But once you're done with your cluster, you can just click create. And one thing I normally do, sometimes I add a key, so a key value, just to specify which of my cluster is development and which one is production. It just helps. So once we're done with that, I've already created a cluster, don't need to create it again. You're going to see the cluster being created and you'll be able to connect to the cluster. So we're going to browse the collection in the cluster. And for those of you who have created a cluster and now you're looking to get your connection string, just click on connect here. You're going to be using the driver, but more specifically, you're going to be using the Python driver. Make sure you have PyMongo installed, and this is going to be your connection string. And you can also get a code example of how you can, in Python, of how you connect to your cluster. And once you have that, you can come back to the notebook and just go through the cells with ease. And one thing to note is you do have to put in your username and your password in the cluster URI to get it to work. So that would just make sure you can find that information over in database access, where you have your user and you have your password as well. So these are all the database. So you would replace the username and then you replace the password as well.
So if we go back over here, I'll browse in the collection. I want to show you the two data sets and what they look like. I've already ingested it, but I just want to show you so I don't keep going back and forth. That being said, we'll probably still be coming back here. Just going to zoom in a little bit. So let's look at the policies first. So when you actually go through when you create your URI, you come into the notebook, you run the cells, it's going to create the database and the collections for you. Here we go. So this is what policy looks like. We have the country for this policy is the USA, and this is a policy name. We have the description of the policy, which is obviously not real. It's just been generated, synthetically generated. And then we have some regulations that are within this policy. And for example, all transactions exceeding 10,000 must be reported to the National Financial Authority. So this is synthetic data, so there's a bit of repetition as well. Generally, I'm trying to just show you, give you like the scaffold to enable you to expand on this use case and build your own solutions. So that's a policy, and we have about 100 policies. But for transactions, we have 200 transactions, and over here we have the transaction information, and we have the embedding as well. This is the embedding we created in a notebook that we have for the transactions, and also we have it for the policies. And this will allow us to conduct that semantic search functionality where we have a user query and we pull in some policies that match the user queries. And we're going to be using that using vector search. Going back to the notebook, we have the policies collection right over here. We have the transaction collections. We've connected to our MongoDB database. And here we have, this is just a cleanup that I normally do for a notebook, just to delete any previous records, because sometimes I rerun notebooks. This is a demo, so I do rerun this a lot of times to try different models or different chunking strategies or different things. So this is a data ingestion step, and when we talk about data ingestion, what I mean is I'm moving data from one place to another. So I'm moving data from this development environment into MongoDB. So we're ingesting data into MongoDB. And how we're doing that is very simple. So we have we're going to create a transactions dictionary, and then we're going to create a policies dictionary. And what this is actually going to do is, we created policies with embedding and transactions with embedding. And we're going to create these dictionaries by just calling the .dict on each of the data of each data point within the models that we have.
Then once we do that, very simple, we could just do an insert many, and we just do a batch operation to actually place in all the transactions and all the policies into a MongoDB database. And that's it. That's like 1, 2, 3, 4, 4 lines of code, data ingestion, done. And that's because we're using Pydantic. We have that document model, that good document data model that is able to handle key value stores, key value data structure that everyone is familiar with. You, me, any engineer you talk to knows what JSON is, except if they're probably coding, even in HTML, you probably know what JSON is. So we've just done 4 lines of code to ingest data into MongoDB. No need for any transformations or whatnot. So once we've done this, one thing we need to do is create a vector index. And what that means is we're going to create a way to essentially conduct vector search efficiently. So we're going to be creating our vector search index programmatically. For those of you who usually tune into this, whenever we do this, we usually show you how to do this on the UI, which would be, you will go into zoom out. You will create your index over here, and you will click on create index, and you click on the JSON editor, and that will allow you to create your vector search index. But today I'll show you how to do that programmatically. So very simple. It's actually quite simple. We're just going to use from PyMongo, we're going to have a search index model, and this will allow us to just pass in a vector search index definition. And that's what we're passing in here. We're going to also pass in the name, and that's it. We're just going to say we're going to create on this collection, we're going to create the search index, and we're going to pass in the vector search definition that we've created. And this is what a definition looks like. So the key thing is the embedding dimension needs to match the embedding dimension that we use to embed data points in the data sets. So that's 256. We're also going to be conducting similarity search, vector search using cosine, which essentially measures the distance between 2 vectors in a high dimensional space. So the distance represents the semantic, how closely 2 vectors are. The closer 2 vectors are, the more closer they are in meaning as well. And here I've added some additional attributes as well, basically to enable the index to be optimized for this particular fields, which are the bank and the sender's bank, the recipient's bank and the sender's bank. And I've done the same for the policy collection as well, because we have 2 data sets. We want to be able to conduct vector search using those 2 data sets. So we need a vector index for each of those data sets. So calling the function will basically not give you an error, because I'm doing this and I've run this several times, like I mentioned. So this is just a duplicate. I've done this several times. But the key thing here is we have our index. Now we can actually do vector search. And the vector search functionality, I'm going to encapsulate it within a function. This function is going to take in a user query, which could be anything, but in our case, it's going to be the embedding of a transaction. We're going to take the embedding of a transaction and then use that embedding to conduct vector search on the policy collection to retrieve any policy that are semantically similar to the transaction. And we're going to see that in a minute. But this function essentially, if we don't have a user query embedding, we're going to return without proceeding with the operations. Now we're going to define the vector search stage. So the way MongoDB works is MongoDB has something called an aggregation pipeline. And those of you from machine learning or data engineering background will understand that a pipeline is a sequence of operation with inputs and outputs, and where the input to one part of a process is the output from another. So you can have pipeline that run in parallel or sequentially. So what we have here is a vector search stage, which is, let's take it backwards. What we have here is the aggregation, is a list, which we're going to pass into this aggregate method, which essentially takes in a pipeline, and we're going to construct this pipeline.
this pipeline consists of the vector search stage. So we're going to take our query right here, and we're going to try to get the closest, we're going to try to look for 150 data points that are semantically similar to this query, but only return the top 5 closest from this vector search operation. Then I'm going to remove the embedding from the returned results because I don't need the embedding. So we're going to exclude it because I don't need it in any further processes in this notebook. And then we're going to add a score as well, just to see the vector similarity score, the similarity score returned by the vector search operation. So we have 3 processes within our pipeline that we can call with the aggregate method. And we have the vector search, which retrieves retrieves 5 documents that are similar to the query or to the transaction in this case. And it retrieves 5 policies that are similar to the transaction. Then we remove the embedding from the documents because we don't need that. Then we add the score, the vector search score, to each of the documents so we can just see the quantified closeness score. And then what we can do is execute this function when we're ready. To simulate a transaction, I'm going to use this transaction model we created earlier, the Pydantic with Pydantic. I'm going to just put in some random fields. And this is just a very simple synthetic transaction. And then what we're going to do here is, the first thing I'm going to do is I'm going to insert this transaction into the collection, just so we have a record of it in our collection. So you can imagine if you have like a bunch of process in a pipeline, you get an incoming transaction. We store this transaction in our collection. When that is done, we have a collection ID. We have the ID of the inserted document. MongoDB returns that from the collection operation, from the insert operation. Once we have that, what we can then do is move on to the next stage, which is we generate an embedding for the transaction because we're going to be doing semantic search. So we're going to prepare the transaction text. We've used this already. We used it earlier on to generate the embedding for our data set. And we're going to then call the get embedding to actually generate the embedding itself. So this selects the attributes to generate the concatenated text, and then this generates the embedding. And what we have is a transaction embedding that we can then pass into the vector search function to conduct vector search against embeddings in the policy collection. And we're just going to get 5 policies back from this embedding. So let's see what this transaction is. This transaction was done for business investment of 500, looks like an angel round. And then it was made through international wire transfer. And yeah, we have the name of John Doe and some fake names and fake IDs. But this is a general structure of a transaction. So what we're going to do is what was returned during the vector search operation, we've stored it in the search results, we print it out, and then we can see the policies that have been brought that are semantically similar. So we can see that one of the policies brought is from France. So this policy is a country of France. Why is that? Well, if we look at the transaction, we can see that the account holder is in France somewhere. And then even though it's from the back of America, this transaction is going into France. So we can see that, okay, there is the reason why that might have been returned is because we have that semantics or the meaning of France captured in this high dimensional space. Then we have other policies that are returned, mostly ones related to France. And there we go. So we've captured all policies related to France. Again, you can experiment with, this is a synthetic data set. You can experiment with different locations of policies and synthetically generate different policies. And what we're going to do now is we've got 5 policies that have been returned that basically our transaction might need to conform to, at least to not violate. And now we can go into
step 7, which is to check if we're violating any of the policies we've retrieved. So we're using Shield Gemma, made by the folks of our Google DeepMind. And what Shield Gemma is a fine-tuned version of the Gemma open model, essentially that is made to enforce policies and outputs out. It's been trained to enforce safety policies, but we can be creative and use it to enforce any policies that we're passing into it. So I'm using the 9B, and there's a reason for that from experimentation. If you use the 2B, it doesn't work as well. Yeah, using the 2B didn't work as well. 9B works, and there's a 27B. B is billion. There's a 27 billion parameter version of the Shield Gemma model, but 9B works just well. 2 billion, not as well. So here, I'm going to go through these functions very quickly. But when we get a transaction and we put it through this policy checker, I want to update the document itself to just update the status of that it's been checked. So we have this attribute is flagged, status, flagged reason, and compliance notice. Compliance team notified. Essentially, this is just going to be a Boolean, which is true or false, and the status as well is going to be violate, compliant, or needs reporting. Those are ones I've just arbitrarily selected. So violation, reporting required, or compliant. Those are the status. And the violation policy is going to be Boolean, is true or false. So does it violate? Is flagged is going to be true or false if it violates the policy. And that's what this function does. It just updates each transaction document. And one thing to note is that's the beauty of MongoDB, because not all transactions will have this field, but when we actually process a transaction, this field can then be placed in. And that way you don't really have to change the schema. MongoDB has a schema that allows for this evolving, it allows you to have an evolving data schema. So we can have documents that have attributes that other documents don't. So here we also have this function to check the transaction policy compliance. This is the key function here. So this function, what it does is construct a prompt. Well, first thing it does is extracts the safety policy from, you can see I didn't change the name from the Gemma because it says safety policy, but we extract the policy from that's been passed into the function. This would be the policy from whichever one we retrieved. And then we also extract the transaction detail. Then we construct a prompt saying tuning or just at least steering the LLM into the role of a financial compliance expert. And then we put in some of the tags for Shield Gemma to indicate the human making a request. So we're going to pass in the transaction details. We're going to pass in the safety policy, which is not the safety policy. But we're going to also add in some prompts as well to make sure we're getting this Shield Gemma model to behave the way we want to. Good old prompt engineering. So after we're done with this, I'm using a GPU over here enabled by Google Colab using T4. And what we can see here is we get our tokenizer, which means the outputs from the model, we pass it into the tokenizer to get the text version of the output, essentially. And then what the model actually puts out. So in the inputs to the model, we pass in the prompt. And what we actually get is, let me backtrack. We tokenize the prompt, then we pass the input, which will be the token, an array of floating point numbers. We pass it into the model, then we can get, I think it's a tuple that is returned that we can then unpack to get the probability of, the incoming transaction violating the transaction and the incoming transaction not violating the policy. Not violating the policy. Then I just set some threshold. This is just me just putting some threshold I think should be enabled for flagging. And then we have a bunch of return statement. So we could return true if it violates, and then we return the scores for yes and no, and then we return a flag saying that it's a violation of the policy. I'm going to skip ahead to an example. So that transaction we passed earlier, that we had earlier, we're passing it into this model, and let me show you where that's being called. So for each policy in the search result the policies we gain from semantic search, what we're actually doing here is we're going to check the transaction policy compliance of that transaction. So we're passing the incoming transaction and we pass in the policy, and that way we can get a score, essentially an indication of if there's a violation. And in this case, there is no violation for every policy based on that for that transaction against all the policy we retrieved. So we see compliant with 88, 89% confidence. So those are the policy we retrieved and its compliance. And this is the yes and no that it's been returned. So here we go. Next, we go over to a policy that could violate the transaction that could violate the policy, and it violates the policy. And I've designed it this way because the amount that is being sent over is 10,000. So the amount that's been sent over is 10,000, and what I'm doing, and each of the policy basically states that any transaction above 10,000 needs to get flagged. So this should be a violation. The previous one wasn't a violation because it was 500. So this one should be a violation, and we'll go to the results. Again, we have the transaction, do the embedding, pull out whatever policies relate to it, and we can see that all transactions exceeding $10,000 must be reported. So we're going to see that we're going to be violating this policy. So very quickly, we move to the violation report, to the output. We can see that we've violated several times the policy that was indicated. And that's it. Now we can detect if a transaction violates a certain policy from a certain country based on semantic search between the transaction and the policies we have in our data set. And that brings us to the end of this notebook. There's no more cells. We made it. So if you watched this far, well done. And what you're going to get is in the description of the video, you're going to be able to access the notebook for this. You're going to be access the link to access the notebook for what's been presented in this video. So what I'm going to quickly go through is the questions. All right, let's see if we can get through some of these questions. I'm a bit over time, but I like to hang out with you folks. So representing the Silicon Valley, I want this guy on my team. I am a one-man team. Thank you, Pedro, for sharing the link. How do we scale vector stores, for example, when each user creates a vector store for their own document? Interesting. I think you mean when each user creates each user creates a document within the vector store. But anyway, in MongoDB, you can scale vertically or horizontally. You can actually scale your database with sharding. I'll place some link over here that can provide you more information on sharding and also creating replica sets as well. But MongoDB scales both horizontally and vertically as well. Let me see if I can get a link to share. If you're still here, I see this was asked ages ago. But yeah, MongoDB is very scalable to handle loads of vectors. Next question. Would searching 256 index be more or less accurate than 1536? Well, depends on what model, right? 1536, it depends on what model. So we use the free small. So you're going to have to experiment. The assumption would be the default answer to that is yes. 1536 of the dimension of the same model would be essentially more accurate because you're capturing more semantics. But then again, the units of accuracy might not be that significant. It might be like 2-3%. You're gonna have to experiment with this to see. But it might not be significant. But what is significant is the dimension size of your vectors when you're storing them in a database provider. So you really want to be making sure that if there isn't much of a significant difference between the dimension size, you're using the lower embedding so you can just utilize a lower memory capacity in your database. More links, and I've used Pydantic library. It's nice to have a document model to model your MongoDB. Thanks for the session. Thank you. In some cases, a single transaction is not a problem, but if you have 20 transactions on the same account for, say, 10 accounts in a given time frame, that is fraud. Is batch models possible? Yeah, you can run. We saw an example of handling batching with MongoDB when we ingested all of our 100 or 200 data points at once. So you can definitely handle batching and process transactions in batch as well. But that's an interesting. So if you see 10 accounts in a given time frame, so yeah, that's just you could just literally check if the same recipient is sending within a certain window is sending a transaction. I'm sure that is something that could be implemented. That's more software engineering, to be honest. But I think that's all the questions. I hope I'm not missing anything. This has been fun. So this is the financial industry. We're saving banks millions over here. And I'll provide a notebook in the link below. And maybe one thing I'll do for the next live show, maybe in the next 4 weeks, I will make this whole process agentic. Why not? Let's do that. We'll make it agentic, so we don't have to click buttons. We just pass in the transaction for a chat interface and let the agent do his thing. It can decide the steps to take, model the transaction, call the retriever, then pass it into Gemma, then get the output, and yeah, do a bunch of stuff. Maybe send an email if we're going to be flagging stuff. That'll be fun. Okay. Thank you guys. And you can always reach out to me on LinkedIn. And thank you for watching.